In this lesson, we will discuss about the vertical and horizontal asymptotes of rational functions. So far, in curve sketching, we have been just discussing about polynomial functions and how to sketch curves of polynomials. What if we are asked to sketch the rational function? For sketching a rational function curve, we need to first determine what are the discontinuities present in the rational functions, and the major discontinuities that we all know is vertical and horizontal asymptotes, and two of the important discontinuities that we all know that are present in rational functions are vertical and horizontal asymptotes. So let's discuss how to determine the vertical and horizontal asymptotes of rational functions and how to determine the end behavior near the vertical and horizontal asymptotes. This would help us to sketch the curve of a rational function. After going through the lesson, the students will be able to use the denominator of the rational function to determine the vertical asymptote. Students will be able to use limits to determine the horizontal asymptote. Students will be able to determine the end behavior near the vertical asymptote, and students will be able to determine the end behavior near the horizontal asymptotes. Let's understand all this with an example. Let's say if we're given a function fx equal to 3x over x squared minus x minus 6, to determine the vertical asymptote, we would only need the denominator of this whole rational function. As we all know, rational function is nothing but a quotient of two polynomials. So the polynomial that is written as a denominator is the one that will help us to determine the vertical asymptote. For doing so, we have to put the polynomial at the denominator equal to 0 and solve for x. Since we know this is factorable, product is minus 6 and sum is negative 1. The factored form would be x minus 3, x plus 2, and that product is equal to 0. To solve for the vertical asymptote, we would put each factored form equal to 0 and solve for x. So we have finally got two vertical asymptotes. One is at 3 and one is at negative 2. To determine the end behavior near this vertical asymptote, we need to make a table of values chart. Now what is meant by end behavior first is, if we have this grid and we plot these vertical asymptotes, x at negative 2 and the other one is at x equal to 3, end behavior near the vertical asymptote means how would the graph behave when it is approaching from the left side towards the vertical asymptote, as well as when it is approaching the vertical asymptote from the right side. Since we have two vertical asymptotes, so we would have to find the end behavior near each of these vertical asymptotes. Let's see how we do that. To determine the end behavior near the vertical asymptote negative 2, all we have to do is determine what happens when we're approaching negative 2 from the left side and when we're approaching negative 2 from the right side. For this, what we have to do is we have to make a table. This is called an interval table. This table would let us know how would the behavior of the graph be when we're approaching negative 2 from the left side. X approaches negative 2 from the left side is mentioned with this negative sign on top of negative 2, and x approaches negative 2 from the right side is shown with a positive sign on top of negative 2. All we are interested in the values that are very close to negative 2 both on the left and the right side. So in the first case, we can take the value that is very close to negative 2 as negative 2.1. The only thing we will be interested is in the signs, whether it is a negative or a positive result. So when we pick negative 2.1 and we sub that negative 2.1 in this function, we sub in x as negative 2.1. The numerator is going to be negative. When we put negative 2.1 here, this part of the denominator will be negative. And when we put negative 2.1 here, this part of the denominator will also be negative. Since we have three negative signs, the final result will be negative. And this is how the final result can be shown. Next, we use a number that is on the right side of negative 2. Let's say we pick a negative 1.9. When we put negative 1.9 in the numerator, we get a negative value. When we put negative 1.9 here, we get a negative value. And when we put negative 1.9 in this bracket, we get a positive value. Even number of negative signs would give us a positive function. So this is how the function is positive. Negative means we are on the negative side of the graph, means we are under x-axis. Positive means we are above x-axis. Since we are determining the end behavior, so this would give us an idea how would the function behave when we are approaching -2 from the left side, and it gives us a negative value. So end behavior would be going downwards. When we are approaching -2 from the right side, and since it gives us a positive value, that means when we are approaching this vertical asymptote, we're going upwards. In terms of end behavior, always remember the value of the function shows us if it is going -infinity or positive infinity. So negative means we are approaching negative infinity. Positive means we are approaching positive infinity. We would repeat the same thing for the vertical asymptote 3. So let's say if we're approaching 3 from the left side, we would put in x approaches 3 with a negative sign and x approaches 3 with a positive sign. So here we are determining end behavior near vertical asymptote 3. We do the same thing. We have 3x over x squared minus x minus 6 that has factors x minus 3, x plus 2. And we would draw out the conclusion here. So when we are approaching 3 from the left side, we will go with the close value to 3 on the left side. Let's say it's 2.9. When we sub in 2.9 in the numerator, we get a positive answer. When we sub in 2.9 here, we would get a negative answer. And when we sub in 2.9 here, we get a positive answer. One negative, that means the final result is negative. So we put a negative here. Here we always have to remember that odd number of negative signs will result in a final solution to be negative, and even number of negative signs will result in a final solution to be positive. Going back to the end behavior near 3, from the positive side would be, let's say if we select the number 3.5, so the numerator will be positive. The denominator first factor would be positive, and the second factor would be positive as well. Since it's all positive, the final function resultant will also be positive. As we know, negative means we're approaching negative infinity. Positive means we're approaching positive infinity. So in this case, the graph would look like from the left side we're approaching negative infinity, from the right side we're approaching positive infinity. The same thing as it was earlier with -2. From the left side it was negative infinity, from the right side it was positive infinity. And this is how we get the end behaviors near the vertical asymptote. To complete the curve sketching for this particular rational function, we need to determine what is the horizontal asymptote, as well as what are the end behaviors near the horizontal asymptote going to be. Now first let's learn how to determine the horizontal asymptote. For any given function, we can use limits to determine the horizontal asymptote. And for doing so, the first thing we have to do is we have to divide both the numerator and the denominator with the highest power of x that we have in the given question. In this question, we have x to the power 2 as the highest power of x. So we would divide both the numerator and the denominator terms with this. And this would look like this. Whatever gets cancelled out, we will cancel that out. So this one cancels with this. This and this gets cancelled out completely. This one cancels with this. We're finally left with 3 by x over 1 minus 1 by x minus 6 by x squared. And we will be introducing limits where x approaches infinity. As when we are talking about the end behavior near the horizontal asymptote, we're always looking at what happens near when x approaches negative infinity and x approaches positive infinity. Therefore, the limit for horizontal asymptote we would have is when x approaches infinity. As when we have to find limits, we have to do substitution. So we would substitute infinity in place of x. For completing the calculation, we always have to remember anything divided by infinity is always a 0. So 3 divided by infinity is 0. We have 1 minus 1 divided by infinity is 0. Minus 6 divided by infinity squared is also a 0. So we are finally left with 0 over 1. 0 divided by anything is 0. That means the horizontal asymptote is y equal to 0. Let's make this horizontal asymptote on the grid. To do so, we would have to make the horizontal asymptote as a horizontal line Because it's an imaginary line, that's why we make it with a dashed line at y equal to 0. The next step is to determine the end behavior near the horizontal asymptote. To do so, we have to approach negative infinity. That would give us the end behavior near the negative side of the horizontal asymptote. And then we have to approach positive infinity. That would give us the end behavior near the positive side of the horizontal asymptote. For that, we can pick any distant value on the negative side. Let's say we pick a negative 100 and we put in the function. So negative 100 times 3 would give us a negative on the numerator. When we put a negative 100 here, we would get a negative. And when we put a negative 100 here, we would again get a negative. 3 negatives will give us a final answer to be negative. On the right side, we can use a positive 100. So when we sub in positive 103 here, we get a positive on the numerator. Positive 100 here, we get a positive. Positive 100 here, we get a positive. Since we have all positive, the final result is also positive. Now, how do we interpret end behavior near horizontal asymptote is, if we have the negative value for the entire function in the horizontal asymptote table, that means we are approaching the end of the horizontal asymptote on the left side, because this represents the left side, from below the horizontal asymptote. So this would be from below. Whenever it's a positive sign, that means we are approaching the right side of the horizontal asymptote from above the horizontal asymptote, because it's a positive answer. So this is how the above arrow looks like. In order to complete the curve sketching on this rational function, we just need to go a step further and find the x and the y intercepts of this function. Let's complete curve sketching on this. We know x-intercept is when y is 0. So if we put fx as 0 and solve for x, that would give us the x-intercept. To solve this further, we would move this over here, so it becomes 0 equal to 3x. So that would give us x is equal to 0, and that is our x-intercept. Next, we would determine the y-intercept, and that is when we sub in x as 0. So this would give us 0 over negative 3 times 2, which is 0 over negative 6. That is also a 0. So our y-intercept is 0. Finally, we will just plot this x and y-intercept, which is 0 and 0 in both cases. And this is where the x and the y-intercept would lie. Therefore, the estimated sketch of this curve would be, you just have to join these end behaviors, and we have to go through this such that the graph follows all the given information. Now, one thing we have to keep in mind when we are making sketches of rational function is that we are already aware of the shapes of the given functions and how the given functions would be drawn. So we would use that previous knowledge that we have gained in the prereq course of advanced functions and apply that knowledge here when we are doing curve sketching.